we are live. So let's see what this. So the video will be. So here to move the slides.
Yeah, perfect.
Yes. Like this. I think we're ready to go.
Okay. Very good.
If you don't mind, get close to him to speak. So
Under the microphones.
Brilliant. Okay, so welcome everybody. Today we have Parth Pavaskar from the University of Potsdam. He will tell us about ISM plasma modes in the ISM. So he's just finished his PhD and will start a postdoc in Pune in India in the coming months. But he did his undergraduate studies in India in Pune, and then he did a master's at the University of Tübingen in Germany, before doing his PhD now recently in the University of Potsdam and with the DESY Institute. But yeah, so today he will talk about plasma modes and MHD and the ISM. So yeah, look forward to this and take it away.
Thank you. So just checking it works. Okay. So hello everyone. Yeah, today I will present this work that I performed during the later parts of my PhD. And essentially I've been told to keep it more easy to understand, assuming not everyone is in the same field. So today we'll go over just the overview of what this project is, what I did, what are the main results, and how we can apply this to real data in astrophysics. Right. So the title is Identifying Plasma Modes in the ISM Using Synchrotron Polarization. So let's start with the ISM. So the ISM is just a multi-phase matter, gas, radiation, everything that exists in the galaxy between the stars and the stellar systems. And there are some things that we know about the ISM from observations. So we know that the ISM is multi-phase in the sense that it contains different thermal phases like molecular clouds, neutral media, and ionized media at different temperature ranges. We know that the ISM is magnetized, and we have seen this through observations of through polarization of synchrotron emission or through Faraday rotation, all of which do require some kind of a magnetic field. And what is probably more important for my talk here is that the ISM plasma is turbulent, and we also see some very characteristic features of this from observations. We see multi-scale energy over power spectra, broadening, non-thermal broadening of spectral lines. We see intermittency and velocity or density all over the galaxy. So naturally, when something has a magnetic field and is turbulent, it's not going to be a simple system to model. It has nonlinearities going on. It has complex systems inside of it. So my study is focused more on the turbulence aspect and essentially the magnetized turbulence aspect in the ISM. So a quick overview of how we quantify turbulence in general. So this is a very typical, a generic power spectra of a turbulence with some scales on the x-axis. So this is the wave number. It's in Fourier space, and then you have energy contained in these Fourier modes. And a typical turbulence, not just in the ISM, but in most systems, not even astrophysical, in laboratory systems, you have some kind of a power spectra that looks quite identical. And essentially, you have a scale which is, so this is inverse. So on the left side, you have larger scales, and on the right side, you have smaller scales. You have, at some scale, you have an injection of energy. then you have a self-similar cascade of energy to smaller scales, and then at some point the energy dissipates, as in it changes the physical description. So when we're talking about the ISM, typically we're talking hundreds of parsecs all the way down to few AU. And then you have the dissipation scale where the energy is dissipated through heat, through interactions with particles, scattering, and so on. And what I want to study is the inertial range. Essentially, it's the entire range between these few AUs and hundreds of parsecs, right? And why do we actually want to study this? Well, turbulence is quite important, as it turns out, and it's important at all scales. It's not necessarily important. Sorry. Yeah. Please feel free to ask questions at any point. I mean, no, okay, that's fine. Okay, right. But that still stands. Feel free to ask questions. Yeah. So yeah, it turns out that turbulence in the ISM has implications for other processes that might be more important to some of you here and might also be important to modeling the galaxy at large. So at larger scales, closer to the injection scale, we have certain effects that turbulence helps in or opposes, such as we have phase exchanges in this multi-phase ISM. The turbulence might or might not be responsible for having an energy equipartition or violating the energy equipartition at these scales. Then you have somewhere in the inertial scale, I assume it says heat regulation. Yeah, so you have heat regulation in the inertial scale where the essentially it is, since you have self-similar behavior in the dynamics, you can have physics that is similar going from the largest injection scale to the dissipation scale. And this is exactly where all of these interactions happen, where uh, basically heat and energy changes hands. You have in this region as well a resistance to cloud collapse. So if anyone here is interested in star formation, this I don't need to explain why this is important. And you also have gas fragmentation. Again, with star formation, you need some kind of fragmentation in the initial phase to form a protostellar disk and so on. So if you do model this kind of cloud collapse with and without turbulence and with and without magnetic fields, you get a wide range of end points. So, and then you have kinetic scales, which is more important for me. Perhaps I don't know how important it is to the people here, but at kinetic scales, you have the turbulence interacting with the particles. And when you talk cosmic rays, when you talk dust grain dynamics, dust grain polarization, when you talk particle acceleration, this is where all the fun is happening. And this is also why it matters what the turbulence looks like in the inertial scale, because initially that will tell us how much energy is left at the dissipation and how the plasma will interact with the particles at this scales. Yeah, so then we come to the point that I would like to discuss, and something that the community does not like to discuss because it makes the picture a more, like, much more complicated, is compressibility. So we know, okay, turbulence is magnetized and turbulence is uh, multi-phase, but the main thing that we have been ignoring so far, or willingly or unwillingly, is compressibility. Turbulence is highly compressible, and this is also something we observe, and we have observed very extensively. So until now, we knew in the solar wind that we do see intermittent structures, we see compressions, we can map magnetic field lines, and we do see changes in the density of magnetic field lines. And this has been observed not only historically but even quite recently in good resolution. And in the ISM particularly, there have been studies now 30 years old that did see density fluctuations uh, quite clearly, but was not necessarily accepted in the community because that makes that adds another layer of complexity to the problem. And as physicists, you want to make the problem simpler, not more complex. But we can no longer ignore this because now you have observations from the Voyager, which has crossed the heliopause, and which has actually entered the ISM, and we do still see density fluctuations. So it's not incompressible. Right. And why does it matter? Why does it add a layer of complexity? Is because the energy cascade itself, the one that I showed you in the previous slide, changes with compressibility. And this we know from simulations, right? And now that we know that observations do show us compressibility, we have to adjust our models accordingly. But before that, we have to, I believe, we have to convince the community more that the compressibility does exist. And this is what I try to do here. Is where my work comes in. That I try to come up with methods that we can actually observe these compressible effects or compressible plasma modes, as I will show you later. So I hope I have convinced you enough that we cannot ignore compressibility and that we do need to, or this needs to be considered in the community and probably should already have been a long time ago. Right. So if we want to observe this, other than the density fluctuations, which might have some other origin, how can we observe this? So uh, classically, the compressibility in magnetic turbulence had a very simple description. It was plasma beta. You have high plasma beta, you have no compressibility. You have low plasma beta, you have high compressibility. That was it. But that is not necessarily how you should define compressibility, because compressibility means you have compressive fluctuations. You have compressive motions in the plasma, right? And the theory of magnetohydrodynamic turbulence actually does decompose fluctuations into two parts. One is a transverse fluctuation that is inherently incompressible, also called the Alfvén mode. Probably most people know this. And then you have this longitudinal and for the most part isotropic fluctuations, which are compressible. And these are categorized in two additional modes called the fast and slow, magnetosonic or magnetoacoustic, depends on how you call it, they're all the same. So essentially, you have three linear modes. So any kind of perturbation in the magnetic field, in the velocity field, in any MHD system can be decomposed into essentially three plasma modes that propagate this perturbation, right? And here is a schematic. So this is also in Fourier space. Essentially, if you have a k, which is a wave vector, so you have a wave traveling in this direction, you have lambda, which is some kind of a magnetic field, and essentially you have these three eigenvectors. You'll see a for Alfvén, slow, and fast. So essentially, Alfvén is in the out of plane component, and then fast and slow are the in plane components. But I will not go into why they are different and not just one component. Is to there are other non-propagating modes that we will not talk about today. So, but trust me when I say that these are the three propagating modes. They do complete the basis vector system, and this is how we can quantify compressibility: is how much energy actually resides in this longitudinal modes. Yeah, and yeah, like I said, the major motivation of this is to show or to observe compressibility, but that is not it. So this we know from simulations that turbulence, when made up of different energy fractions of these modes, has different properties and can help with different processes. So, for example, Alfvén mode turbulence, it is more efficient at transferring energy along the magnetic field. So, this is especially important in systems like the solar wind, where you have a clearly defined magnetic field direction, and you have an anisotropic interaction with particles, right? You have particle scattering through a process called gyroresonance, where the particle gyro frequencies match up with the wave frequency. So it's kind of like a nonlinear Landau interaction, and so on. I will not point them out. Similarly, the compressible modes, slow mode in simulations has shown that it is highly efficient at forming cold neutral media from warm ionized media. And this is also a nice thing, because so far it we don't really know how the cold neutral media forms in such a large amount, and maybe the slow mode does answer that. I don't know, it's not my field. uh, yeah, and then you also have the density fluctuations that I showed before. It has also been shown that, especially in high beta, slow mode is responsible for driving these density fluctuations. And again, for star formation, these density fluctuations are important because they are what lead to the fragmentation of these clouds. And the main part of my work was the fast mode. Essentially, the subdominant mode almost always ignored by everyone, the middle child, whatever you want to call it, never considered, right? I mean, it makes sense. Why? Because in pretty much any kind of simulations you make, the highest energy you will get in a fast mode is 20%. Probably that's like the best case scenario. So it makes sense why the community has neglected it so far, because we just don't see it, right? But if you do have some simulations where you somehow do get a larger fraction of fast modes, you see some very interesting effects. So essentially, the pressure fluctuations. So we saw density fluctuations, but it has been shown that only the fast mode is able to actually drive pressure fluctuations in non-ideal MHD plasmas. You have magnetosonic shocks. So anyone who works in particle acceleration know that we need shocks to get most of the theorized acceleration mechanisms. And there is this effect called the transit time damping, which is another resonance interactions that apparently only the fast modes dampen to provide energy to the particles. And it has been proposed that this might be the missing key to DSA theory. Hasn't been proven so far, so who knows. But my point being that depending on which mode dominates the energy in the plasma, you can have very different interactions at this volume. And this is something we really should be working towards observing, because simply observing a plasma doesn't tell us what is happening inside the plasma, right? So yeah, so it would be nice to have a method that actually differentiates between these plasma modes when we observe it. Yeah, this is a nice tagline or whatever. Anyway, so can these modes be observed? But sadly, no. And if they could be, they probably would have been already. You cannot observe them directly because, like I said, these are decomposed fluctuations, and not just decomposed, but decomposed in Fourier space. So in real space, it's you just see a plasma, right? You don't know what's happening there. So there are no direct observables for this. But there was a paper in 2020 from Zhang et al. That actually did find out quite from an empirical method that there is this the Stokes parameters of synchrotron polarization somehow do contain some kind of information about which mode dominates the energy. And how they found this out, I don't know how, but how they showed that this works is they basically took this parameter, which is now this I plus q divided by 2, took the variance of this parameter and just tested this for different lines of sight for synthetic observations. And then they found out that when they had Alfvénic turbulence versus non-Alfvénic turbulence, suddenly this variance of this parameter looked different. And this was a key. We don't know why it looks different, but it looks different. And if you are only worried about observing these effects, you don't care why it looks different, right? You just want to, as long as they look different, we can observe it. So this is the parameter that I also used in my work. And essentially the idea is that you have some magnetized turbulence with some composition of these plasma modes. You have the synchrotron emission from there, which is polarized, and the polarization ideally traces the local magnetic field. You have these Stokes parameters, then you observe these Stokes parameters, you get a signature, which is, like I said, the variance of this epsilon, and then you try to make comments about how the local turbulence at that source looks like. So I will show you in 4 simple steps here how to get this signature. So essentially, you have imagine you have a region of interest that has some lines of sight, and with each line of sight there is an associated set of Stokes parameters, the synchrotron polarization parameters. And then you can also compute a mean polarization angle inside your region of interest, so which I show here with this vector p0. Then you define an arbitrary vector shown here by this red arrow, and we call it the Stokes frame because it sounds nice. But it's completely arbitrary, and it makes an angle phi s with p0, and then you rotate the Stokes frame so that it goes from p0 to minus p0. So essentially you have phi s ranges from 0 to pi, and then each rotation you compute this function that is now called sxx for legacy reasons, is basically variance of I plus q. What I showed you, I just removed the 2 here because it doesn't matter. And now, of course, when q, you would know that q and u are already rotated parameters. So once you rotate your Stokes frame, you also have to correct your q, which is given here as this q rotation. It's just simply q cosine of phi plus u cosine of phi. So that's what you do. You define this red line, the arbitrary vector, and then you rotate it. At each rotation, you compute the variance of I plus q, and that gives you what we call the SPA signature. In case I didn't mention, this method is called the Synchrotron Polarization Analysis, so SPA. And this is a sample of what this signature looks like. So on the horizontal axis, it's again phi s. So as I said, it goes from 0 to pi, and then you have this sxx function. And I don't know why it looks this way, but yeah. So here I show two samples: one for purely Alfvénic turbulence, and one for purely compressible turbulence. So these are from synthetic turbulence. So this is not an observation or something, just a representation of how the signature looks like when we have these two modes, or we have an Alfvénic and non-Alfvénic turbulence. And theta lambda here is the inclination of the line of sight with respect to the magnetic field, so the local magnetic field at the source. So naturally, when you see the difference in the, essentially when theta lambda is 90, I assume it means that the magnetic field is pointing towards you, so it doesn't matter how you rotate, your frame is anyway pointing towards you. Yeah. Anyway, so this is how the signatures look like, and you will see that there is the structural form is quite similar, but especially at this phi s equal to pi by 2 region, you will see that you have this valley feature that changes width. Apparently, the Alfvén mode produces a narrower valley, and the compressible mode produces a wider valley. And this is exactly what they also observed in the original paper, and I computed this with a bunch of different simulations, and we did find out that this still happens. So it was not a fluke or something that they fabricated, but yeah, it did show up in my calculations. So essentially, what we call this the concavity is basically the width of this valley region is different when different modes are dominating the energy in the plasma. And this is exactly what we want to calculate. So or rather what we want to quantify. So if we do have synchrotron polarization observations, we get these signatures, and then we would like to quantify this so we can actually make a recipe for what differentiates these two signatures. So okay, so this is one feature, the concavity, and then during my tests I also noticed that some of the signatures, especially when the turbulence was fully compressible, appeared to be asymmetric, which is at first sight would make no sense to you, because we just rotated the Stokes frame from 0 to pi, so it should be symmetric, because then if it's asymmetric, it means that the contribution from the orthogonal magnetic field component is non-zero. Again, makes no sense. But we did see this, and this was not again not a one-time thing, because this did appear in quite a few compressible simulations. And then I asked, why does it appear, and why does it only appear in some simulations and not others? So perhaps it is not a numerical artifact, and perhaps it is actually a feature in the observation. So this is also something that we chose to quantify to see if this does actually have a trend with the mode energy fractions. And this then leads us to quantifying these features. So how do we quantify? Well, the easiest solution is to fit the observed profile to something that fits it, and then quantify the fitting coefficients, right? So the fitting function that I chose was a simple geometric expansion of variance. So it is just a sine and cosine expansion up to the fourth power here. and really doesn't make sense which function you choose, because the end goal is just to fit it to quantify the coefficient. So as long as the any function fits the signature, it should work. Yeah, and then if you remember the signature, you will see that it looks cosine like if it's symmetric, and it looks sine like if it's asymmetric. So essentially we can say that the cosine coefficients contain the symmetry part of the signature, and then the sine coefficients contain the asymmetry part of the signature. And that gives us, after fitting uh, four coefficients or four free parameters, but of course we can just renormalize so all three of them to one. So essentially we are left with three, right? And this is exactly what the SPA method uh, classification parameters are. So you have this first ratio, which is the A4 to A2, essentially the cosine coefficient ratios that quantifies what I just said was the concavity near this phi s is pi by 2. And then you have these two coefficients normalized to A2 that quantify the asymmetry. Well, we don't know at the moment if they are important, but we will fit them anyway to see. Right. And now, okay, so now we have some semblance of a recipe, but we have to actually test this. And we cannot test this with real observations because we don't know what is happening at the source. We need a controlled volume against which to test it. So in this case, of course, uh, the natural next step is to make some simulations with plasma turbulence. Then we control the simulation, so we can drive them in a way that we control the mode fraction. So here I just want to show you this plot from this paper, Makwana 2020, where they showed how different driving changes the energy mode fraction in the simulation. So the S prefix here means solenoidal, essentially divergence free forcing, and the C means compressible, so curl free forcing. And you see then the fraction of the three modes in these two bars. I believe the left one is kinetic energy and the right one is magnetic energy. And you will see quite clearly when you have a solenoidal forcing, you have most of your power is contained in Alfvén and slow modes. When you have compressible driving, you have a decent fraction of fast modes, right? So this is exactly what we would like to do. We would like to construct some set of simulations that have two different uh, mode dominances. So one that is dominated by Alfvén mode, one that is dominated by compressible mode, and then we test our method against it. So this is what I did. I will show you the details of the simulation in the next step, in the next slide. Yeah. So what is our goal here is to simulate plasma turbulence that resembles the ISM. We generate some synthetic polarization, and since this is a single fluid simulation, we don't have any electron number density here, so we assume that this is constant. Of course, it's a crude assumption, but one done to save computing resources. And then we have this fairly simplistic description for the Stokes parameters for the synchrotron polarization. And then I don't know why it says one. Is step 3 is to test the method with the simulations where we know the energy fraction, so we know how well the method works. So this is what I did. So I have a set of 3D ideal simulations using this code called Athena++. So we essentially we simulate 3D periodic box simulations with a isothermal equation of state. We have third order time and spatial integration. We evolved the turbulence long enough so that the energy is saturated, so it resembles more the realistic ISM where the energy has saturated since it's been injected for so long now. And then I make a set of 16 different simulations, and I divide them in two categories. As I said before, I have 8 with solenoidal forcing, which I know are Alfvén dominated, and then I have 8 with compressive, which I know are compressible dominated, which is essentially slow plus fast. Right, and it's just a visual difference of what the driving does. So here I have two simulations, essentially all parameters identical except the forcing field, where here it's divergence free and here it's curl free. And you see quite clearly how much this changes not just the structure but the isotropy, so here your density and magnetic field is highly correlated. It has an isotropic structure along the magnetic field, while in the compressive case you have some non-correlated regions, you have some density gaps or voids, bubbles, whatever. So it's just a way of showing that just simply changing the driving mechanism, which does happen in the ISM. The ISM driving is not homogeneous. Energy is injected through supernovae, through stellar outflows and whatever. So simply changing the driving mechanism does change a lot in the how the turbulence looks like. Right. And this is then a sample of a polarization map where I plot the background gas density here from a simulation and the resulting polarization vectors here, where the length of the vector shows the polarization degree and then the direction. So these kind of maps are what we will use to test our method against a known set of parameters from the simulations. So let's jump to some results. So first I want to show you about the quantification of this concavity parameter. Essentially what I told you is able to separate Alfvén and non-Alfvén plasma turbulence. So if you remember, this was the parameter that I promised you does quantify this concavity, is A4 by 2, and it is plotted against theta lambda, which is again the line of sight inclination with respect to the magnetic field. So we also want to scan this because in real observations, most of the time we don't know the inclination. So we have to cover all possible orientations. So first I will only show you the incompressible simulation. So if you remember, we expect we expect only Alfvénic turbulence to be dominant in the incompressible simulations. So if we do use our method, we expect it to show something that is unique to Alfvén turbulence. And the simulation itself here is represented by this blue curve line, whatever. And the other three are the idealistic individual modes. So essentially, now I know that my blue line is Alfvén dominated, so I would ideally want it to be similar to the yellow line. As in, the similar it is to the yellow line, the better the method works, or the more confidence I have in my method. And the two lines here, well, they are not exactly identical, but compared to the other modes, where you see the slow mode, which is constant, and then you have this the fast mode, which I don't know what it's doing, but compared to this, you see fairly similar behavior. I will not say exactly identical, because there is, if you look at the error bars, which are simply from the large parameter range of my simulations, you will see the error bars are quite large. So we cannot say with 100% certainty that this is identical, but it's good enough given that the alternative is nothing, right? So yeah, so we expect, like I said, in the signature, a narrow valley, which means we expect analytically from our fitting function this A4 by A2 to be less than 0. And if you look at the Alfvén mode, which is the yellow, you will see that it is in fact 0 for all the magnetic field inclinations, while the simulation itself is close to 0. It's negative in some cases, but not in all cases. But given the width of the
physical quantity.
Right. No real reason. Like I said, the reason for using the source parameter is purely empirical. So I'm sure if you trial and error a bunch of different parameters, some of them might hit the mark. So there's no reason for choosing one over the other as far as this specific method is concerned. I'm sure there would be, in some cases, the angle itself would also give you some information. I'm not sure how it would differentiate between the modes, essentially, because the angle would give you trace the local magnetic field. What happens?
See, this.
There's a feedback.
Yeah, but they were removed.
Okay.
Sorry.
No problem.
It's just observationally, basically, Stokes Q will vary with frequency, with parallel
Right.
effects, but you could define the intrinsic angle as related to the magnetic field direction.
Right. I mean, yes, I agree with this point that observationally the angle is more universal in the sense that it is less sensitive to frequency or even to Faraday rotation. Maybe not. I don't know. But I would say but I would assume that the I would also be equally sensitive as Q. I'm not completely sure on this from the observational perspective. Or
Yeah, I would be much simpler behavior, just a power law behavior with frequency.
Right. Okay. Yeah.
Whereas Q would be oscillating possibly with frequency,
Mhm.
Faraday rotation.
Right. Actually, yeah, this is. I mean, like I said, in this particular case, there is no reason why we chose this other than it was shown to be empirically to have some kind of this differentiation. But perhaps this is something that could be checked or should be checked in a sense. But when we did this work, we did not really have at this step real observations were not involved. So this is again I and Q in the most idealistic description, where Q or rather they are consistent with uh, like across lines of sight or across frequencies, let's say. But yeah, of course, when applying anything to real observations, I'm sure there are things that we don't take into consideration as simulation people. But yeah, this is something maybe I need to consider more if the angle itself can, because I mean, in a sense, the angle is quantified because U and Q essentially gives you the angle, right? Is the arc tangent of
Included, like physical effect must be in the angle or in like the curl or divergence
right.
of the field. So there's like
Could yeah, I mean yes, but yeah, maybe, but I couldn't give you a statement on if it will work or not, because also the angle would then we take a ratio of U and Q, so perhaps there is a if there is a feature in both of them, it gets cancelled out in the ratio. I'm not fully sure.
yeah, the C and D people use the E modes and B modes.
Right. Yeah. Yeah. Right. Yeah. I think E modes and B modes were also considered for the original paper here, but I'm not fully sure where they landed with this. But yeah. Okay. If it's okay to continue. Okay. Yeah. So I don't know where I was, but I assumed I was telling you that the total B here matches much more nicely in the compressible case than it does in the non-compressible case, right? And here I would ask you to compare the blue line here with the red line, slow mode, which we know for a fact dominates the compressible simulations. And now we do see that this blue line itself, including the error bars in most cases, does actually lie above zero. Uh, so it seems that while the method might not correctly identify Alfvén mode turbulence in all cases, it does identify the compressible mode cases, which is nice because that is what we want to observe predominantly. Anyway, right. Now this ran out of battery. I'm not sure.
Yes, that.
All right, that's yeah, that's fine. I think should be perfect. Okay. No, no, it's okay. It's okay. It's not a problem. Yeah. Right. So this gives us a recipe. Now I showed you that we do have this clear differentiation in how this A4 by A2 parameter behaves, and it does seem to somehow obey this recipe here, that when the plasma is dominated by compressible modes, it seems to be positive. When it's Alfvén modes, it seems to be negative most of the times. So the method works in this case, at least in simulations. At least it's always a big caveat that if something works in simulations, not necessarily in real observations, but it's a good start. We can definitely show that the method works in simulations. But then I also promised you that we would analyze this asymmetry that was not considered in the original paper. That was, all the signatures were assumed to be symmetric in the original paper. So we chose to not have this assumption. And then I basically calculated both of these A4 by A2 and B4 by A2 parameters, essentially the sinusoidal parameters from our fitting function. And I plot them against the magnetic field inclination again. And now we try to see what this means, right? So the parameter itself, when it's zero, it means there are no sinusoidal components, so the signature is fully symmetric. And then any deviation away from zero in either side means that the signature is asymmetric, either right or left of pi by 2. So essentially, we don't care what the value of B2 by A2 is, if it's negative or positive. We just care how far away it is from zero, as in how the absolute of B2 by 2 or B4 by 2 behaves, right? So again, we have these three control volumes where they are just decomposed modes, and then we see that pretty much all of them seem to lie very close to zero. But now like I said, since the distribution is symmetric, even if there is a large statistical uh, width to the Gaussian, the mean will be zero. So essentially, now we want to look at the error bars, because they tell us how wide this Gaussian would be if I plotted this as a PDF, right? So you will also see that, okay, the yellow curve, which is the Alfvén mode, does seem to have slightly larger error bars. But suddenly now the green line, which is the fast mode, which I didn't talk about before, because as I said, it is always subdominant in the simulations, suddenly now it shows large amounts, extreme amounts of asymmetry, especially at large inclination angles. You suddenly see this green error bar going out of the plot here. And this is actually good news for us, because for once, and probably for the first time, we have something that only the fast mode seems to do in observations. And we have, for once, a recipe that can separate fast mode from not fast mode, or rather that can, incompressible turbulence, it means that it can separate fast mode from slow mode, which has never been done before. I'm not claiming that it can be done, but it's, maybe this is the first step towards this, right? So this is the nice, probably the nicest result from this work, is that the fast mode does seem to show this asymmetry, and this asymmetry was not a numerical artifact. It was essentially uh, only appearing in simulations that had a significant energy fraction in fast modes. So this is something I think is the main, I would say, the main result of this method. And then, yeah, we have this method, and here I also added some pre-processing steps in case we want to apply this to real observations, right? So in real observations, we have these Stokes IQU maps. First, we want to estimate some kind of correlation scale or coherence scale for the turbulence, because naturally our region of interest needs to be smaller than this coherence scale. So for this, we use typically the structure functions to get the coherence scale of turbulence. Then we define our area of interest, and then we follow the method that I showed before. We calculate this the signature function, we fit the function, we calculate the coefficients, and then depending on where the coefficients fit in, we classify the mode dominance. And I didn't explain before, but I'll go back a slide. one thing that you will see that not only is the fast mode error bars really large, but they're also only large at large inclination angles. So perhaps this gives us a two-way conclusion. If we do find this, is that not only if we do find large asymmetry that the fast mode exists, but might also be that the magnetic field at the source is at a large inclination angle with respect to the line of sight, because at lower inclinations even the fast mode doesn't show asymmetry. So this is in a sense even nicer, because it might give us twice the information, not only about the modes but also about the local magnetic field inclination. So this is also what I show here, as in if you do have compressible or slow mode, or MS is magnetosonic compressible. If you do have compressible mode dominance and asymmetry, it could not only mean that the fast mode is present, but it could also mean that the line of sight inclination angle with the magnetic field is. But of course, this is a maybe, and yeah, which is. So this gives us like a nice general recipe for this method. And then, well, yeah, when we think about using or applying this to real observations, we have Faraday rotation. So everything I told you until now assume that all the polarization traces the local magnetic field. But then you have this thing called Faraday rotation, which makes sure that you never trace the local magnetic field, right? So we tried to see how this would change our method, or how this would affect our method, right? So this was a very crude implementation, a very last minute thing I did. But what I did is now I have my simulation from which I calculate the synthetic observations, but then I have a large foreground volume. And essentially the foreground volume doesn't emit, but all it does is rotate the signal that originates from the simulation. So essentially it is a Gaussian randomizer in the foreground that has this sigma here is just the standard deviation of the Gaussian function of this foreground randomizer. So essentially larger the sigma, more the randomization in the observed polarization angles, more errors in the traced magnetic fields. So you see here again with increasing Faraday rotation, you see that now our previous method that had a nice demarcation at 0, suddenly all the values are now negative. But if you remember, the compressible mode that we identified, which was the main goal of this method to identify, was always positive, which means that the Alfvén mode, which is negative, could be mistaken to be compressible mode, but the compressible mode can never be mistaken to be the Alfvén mode, because you will see that with increasing Faraday rotation, all the data points just seem to go lower. So it's a one-way error. So no matter how high your Faraday rotation is, no point will travel upwards. So if now I observe something here, I know it has to be compressible, because the only way it could go is down. It could never pass from negative to positive, right? So it seems to be that even the errors are in our favor, in the sense that they only misclassify Alfvén mode and not the compressible mode. So this is of course, this is a very simplistic implementation of Faraday rotation. Naturally, in real life, you have the foreground layer which also emits. So it doesn't only rotate or depolarize, but it also emits its own polarization. So perhaps we need better models on how Faraday rotation works in this case. But in this simple model, at least, it does seem that it will not affect our detection of compressible modes. Right. And then this is, I think, the last slide. Yes. Is application of this method to real data, perhaps what is more important than the method itself. Right? And this is a work that I did with Sunil here last year, where we tried to analyze the magnetic field and the turbulent field in the Cygnus loop region, which is essentially this map shown here, where we divided the region into 3 sections that we thought had some interesting structures in the polarized intensity maps. And then we applied the SPA method to find out if the turbulence inside is actually compressible. And here are the 3 regions that you see in blue, red, and white is essentially these three regions overlaid with these circles, where the green circle means it detected an Alfvén signature, the red circle means it detected a compressible signature, and if the circle has a tiny dot inside, it means it detected asymmetry as well as the compressible signature. So one thing that you will see is a large lack of dots, which might indicate to us that the inclination of the local magnetic field there is not so high. Might be high, but this indicates that it is not so high, which is one nice result. You will also see that we do actually see a significant fraction of red circles, and I have applied this method to multiple regions where we saw none. So this is not simply a 50-50 statistical random error, but in fact we do see a significantly large fraction of compressible mode signatures from this region, which also agreed with the result that we wanted to put forward. This is in fact not one but two separate objects, like two separate supernova remnants that are now interacting, and these interacting shock waves do actually create compressibility in the local turbulence there. So this was our result from last year, and this was a direct example of application of the SPA method to some real data. And if you have questions about the observations, I'm not the person to ask. He's right there. But yeah, so my part in this was doing the SPA method with this data. So yes, please.
If you don't know the inclination of the magnetic field, how can you find the features of one or the other? Because you would need.
Not necessarily. So if I go back, if I go here, essentially our not this plot, sorry, this plot. We differentiate our method based on the value here. Doesn't matter where, let's say you're observing somewhere here. Doesn't matter. We differentiate based on the value. So this is just to see if our method works for all inclinations. Like clearly, you would say that the method doesn't work here, right? If your inclination is so small that your magnetic field is almost aligned with the line of sight, nothing works, as you can see. So the point of showing you this plot as a function of theta lambda was to show that you still have some range where the method works. So we don't need to know the theta lambda. As long as it's not aligned with the line of sight, you should be okay. So that was right. It's basically the value as in larger than zero. So smaller than zero. Of course, it's not. We do have some essentially some error range that we don't say that larger is one, smaller. We have an ambiguous range. So if it's very close to zero, we just say it's ambiguous. We refrain from making any comments. So the points that you see are so the points that are missing essentially is ambiguous. So rather than say one way or another, we chose just simply not to say because we are not sure ourselves. But the points where you do see the circles is that we are confident enough to say that the signature was one way or another. So that's essentially it. Yeah, and I think that is my last slide. So thank you very much for listening.
Observe the synchrotron radiation, you know there has to be a significant component of the magnetic field.
Right. Yeah.
Yeah, so there's some significant perpendicular.
Right.
So that, it's not all zero. It can't all be 0 degrees. So
I mean, it also cannot go 90 degrees because then, actually, it can probably. Yeah, but then it's just perpendicular. Yeah, sorry.
Okay, yeah, questions?
Yes.
Thank you. A couple of questions. Have you tried to fit the profiles to Gaussian integral decomposition? Because some of them look like the
Right.
kurtosis will directly tell you.
Right. So essentially, as I said, it's arbitrary which fitting function you choose. You just want to quantify the features, right? So anything that fits well enough is good enough. So this was our original thought process, right? Yes, I can have nicer looking, or like you said, kurtosis is a very obvious similar looking function there. But essentially, yeah, what we wanted is, since it's a variance, so any function that has the fourth order coefficients, it will work. And we have actually checked this. We have checked with different, basically like a Taylor expansion. It works. It works just as well. So.
But do you really need to go to such a high order with so many parameters? I just wondering whether you could introduce some kind of errors or error bars just by using redundant parameters.
I believe for fourth order you do, because it's simply variance squared. So it's essentially variance of I plus Q, which is, if you think, if you remove the integration, is basically B squared or B perpendicular squared. So it's variance of B squared. So it's naturally a fourth order in B. So this is just a back of the envelope thing that we thought that perhaps then you do need to go to fourth order. I'm not sure if lower order would work, or that there is some redundancy here. Could be, but yeah. If it, we decided if it worked, don't touch it. So.
Another thing, if just to, because it's not my thing, so it's sometimes hard for me to visualize everything. So when you compute the variance, basically, I don't know if it's something that's circle, but you have to compute an area, right? To compute for every single point.
Right.
So those 4 points that you put, you have to put, in this case, you will have the variance of 4 points.
Of 4 points, yeah. So essentially, as many lines of sight as you have in that region of interest, yeah. So this was just a representation.
And in the last plot, sorry,
no, it's fine.
In the last plot, did you check, I mean, just for fun or whatever, if there is any correlation whether they are green or blue with the polarized intensity, because it looks like the edges.
I believe we did do something like. Right. So I believe we did do something, but we couldn't find. We weren't confident enough to say this. So.
The first thing I noticed.
So especially here, where you do have a higher intensity. I mean, this kind of makes sense because this we relate to the shock front. And then the shock front, we also expect compressibility, because this is like the most intuitive thing. But for example, with other regions, I mean, you have some, but in the end, we decided not to make a comment because we were not fully confident about it. It's rather say nothing than be wrong. So it was more that, but I'm sure there is. It's not purely statistic. Like there is some correlation there. Perhaps we need a higher resolution observation that we can actually. So as you see, so I have marked these squares here, and that is essentially the I forgot, it's for the Wi-Fi, never mind. But yeah, for each point, essentially the variance was computed over only a tiny square around that point, right? So there's not that much statistics in the variance itself, so it's probably what, like, I would say 30, maybe 8 squared or something like this was the so 64 points. So I'm sure there is a correlation, but yeah, we would need more statistics.
How big is the beam there?
I mean, this is a good estimate of the beam.
Yeah, you can kind of see the individual pixels. Yeah. So I believe this whole map was, this was what, 80 by 80 lines of sight or so in this map. So there's not that much statistics to begin with. So. I mean, compared to my simulations, I think this, so it's always a case of this methods. Yeah. So
we have a better resolution for Parth,
but that's a 21 centimeter.
Yeah. The Faraday protection will
Right.
affect that
Right.
at 21 centimeters. So these are the 11 centimeters.
Right.
So that's why we compare the Faraday protection will do all the results.
Yeah.
Other questions?
Is there any question online? If so, please just unmute yourself and make your question. We will hear you.
There's nothing in the comments also.
So let me check
So very bright, in some cases very well resolved synchrotron sources are radio galaxies.
Mm-hmm.
Is there, a strong motivation to try this?
Right. So the limitation here is, as I said, you need to. So this variance, the upper limit on how big your region can be is the coherent scale of turbulence. So essentially, as long as you resolve enough so you are much smaller, that you're confidently smaller than the coherent scale, this should be applicable in these also radio galaxies.
Yeah, so it
Right.
seems applicable to
Yeah.
all areas.
I mean, the bottleneck is resolution essentially. So there's nothing physics that is telling us not to do this in radio galaxy. Yeah.
Maybe for with the escape.
I'm sure there's PLA maps that have kiloparsec scale resolution of hundreds of
Mhm.
kiloparsec scale lobes, radio lobes.
Right. I guess another bottleneck is also how strong the polarization degree is, because again this is highly dependent on that. So.
Yeah, which brings me, well, we can chat afterwards.
Sure.
But again, with the Q parameter, so like if it is the polarization angle,
Right.
if you can convert it to this, you can just immediately correct for Faraday rotation.
Right.
Just use the intrinsic angle. That's
I'm not sure how you would correct for Faraday rotation, like for foreground or for depolarization, essentially, because you have an angle, but the more Faraday rotation, yeah. We discussed doing this with multiple wavelengths. So essentially, if you have two wavelengths, observations from two wavelengths, you can kind of compare, because then the Faraday rotation itself will be dependent on wavelengths. So we did actually discuss it.
We need the Faraday rotation with the full map. So like for this particular source, we have the Faraday rotation map for some chunk of it.
Right.
Because the SNR for polarization is not good for
Right.
determine that path, and that's why that will break down. I agree that we can correct at every pixel, we can correct the polarization angle for the FR, but we need to have the
RM.
Okay, yeah. That's a longer discussion, but yeah, let's thank Parth again.
Okay.
Very nice talk.
Thank you.
You are around tomorrow?
Yes, I'm here. I'm here tomorrow as well. Yeah. Yeah. I don't.
256.
The other one ran out of battery, so I had to swap them.